Thank you very much, and thanks very much to the organizers for setting up such a nice conference and for inviting me here. What I want to present is joint work with Joanna Koman, a PhD student of mine who's just finished, and Eli Pomoni. And to get started, let me recall some of the standard motivations for studying topological string theory, which, well, on the one hand is that it is of interest both for physics. It gives terms in effective Sura actions, Nekrasov partition functions, and much more. Most of you will be very much familiar with that. And as well in mathematics, where it is related to a good part of the modern theory of enumerative invariants, Gromov-Witten invariants, Donald-Thomas, Obakuma-Watha, and so on. And there are various approaches to its computation. I just name a few: topological recursion, holomorphic anomaly, topological vertex. And most of them are perturbative in one way or another. Some others are not. There's, for example, a matrix model, which in a sense is non-perturbative, and there's the work of Marcos Marinho and others I would like to mention. But yeah, part of the goal will be to propose a non-perturbative definition for some cases where, to my knowledge, it hasn't been done. All right, so let's define the class of models or of Calabi-Yau's we want to consider the topological string on. This is what I will call the class sigma, local Calabi-Yau's defined by some equation. Defined by some equation of this form, very simple, where we have a polynomial. Well, we can generalize it such that this is just a local equation with a variable v squared and some q, where underlying the whole story is a Riemann surface C. In general, it may have arbitrary genus, arbitrary number of punctures. To be specific and, well, where most of the thing is actually worked out, I shall restrict to genus 0, but this does not seem to be so essential here for my story. In which case, we can represent here this. I mean, this is then just a quadratic differential on a Riemann surface, and we can represent it very explicitly in the case where we have genus 0 surfaces underlined. So, yeah, we have some terms. Just maybe it's good to memorize a little bit the parameters which are introduced in this way. There are the coefficients of the second order poles called delta and coefficients of first order poles E. And yeah, so this class is called sigma partly because that is when we want to study theories, gauge theories or supersymmetric field theories of class S via geometric engineering in the context of topological string theory. So, well, that is what may motivate also sigma as a terminology. Well, and in this context, there's a very well-known and very nice relation between the curve, which is defined by this very polynomial defining the Calabi-Yau in first place, and the Seibel-Witten curve describing the low energy physics of the associated gauge theory. So, yeah, it's just like that. It's a curve in the cotangent bundle of C, this Riemann surface, which is underlying everything here I'm talking about. And our problem, that's what we want to formulate on this slide, is to define and compute the topological string partition function for this class of theories. All right, so, yes, that's that. Okay, let me remind you of another thing that is well known, which is useful for me to set up relevant notations, which is local mirror symmetry. So I've been describing the representation in what is called a model, that is as a complex curve. There is a mirror dual to that, which is called X. And so then, what was, maybe I go back one more time. So the parameters here, these are these deltas, the E's and the Z's. All this is now collected, that is now collected in this complex structure moduli, that is the tuple of all these variables, okay? So these are the complex structure moduli on the B model side, and of course associated on the A model side, I have scalar moduli, which I can compute concretely by evaluating the periods of the canonical one form on this surface sigma, which is the double cover of the underlying curve C. And say, yeah, a little more concretely, our problem will be to compute Z top, the topological string partition function, as a function of, well, the Kähler parameters as well as lambda, which is here notation for the topological string coupling constant. All right, so to motivate the approach that we will be taking, let us quickly discuss some work, well, a couple of years ago by Dijkgraaf, Holland, Sulkowski, and Bafa, who were using a chain of dualities which relates the geometric description, which we basically introduced just before, as type 2B string theory on a top nut times this local Calabi-Yau Y, which is defined by this equation we've seen before, to other dual descriptions. So this is what is would be going, or well, rather the mirror dual would be growing, associated with the theory of Gromov-Witten invariance. Then there's the theory of, well, there's a D-brane picture. I don't really want to go through all this in great detail. The main point is, okay, there's a dual picture mathematically associated with Donaldson-Thomas theory, where we have a surface in the compact part, or in the, well, in the rest of the background, which is the mirror dual of the surface Y. And then one does the counting of D0, D2, D6, or D0, D2, D4, D6, and so on. You know this perhaps rather well. And the third and most interesting player in the game is then what was called I-brane by the authors above, which is a type 2A string background with a D4 and a D6 intersecting along that very surface sigma, which is the key player here. And then chasing these dualities, you can trace what happens to BPS states and their generating functions. So this gives relations, and we'll have to formulate this a little more precisely in a moment, between, well, the generating function for Gromov-Witten, the one for Donaldson-Thomas, and this so-called I-brane partition function, where, by these authors, it was argued that it can be represented as the partition function of a free fermion system on sigma, basically representing the massless open string stretching between D4 and D sigma. And one of the most interesting aspects of this proposal is to understand what happens when the topological string coupling is turned on. This will, following the chain of dualities here, correspond to turning on a B field along the D6, and it leads to a non-commutative deformation of sigma, which will be called the quantum curve. All right, so the proposal that then was formulated by Dijkgraaf et al. Is a little more precisely formulated in this form. The relation between the free fermion partition function and the topological string partition function takes the form of a sort of Fourier transformation, where one is summing over some charge lattice here, and one is shifting the Kähler parameters on which the topological string partition function depends in a specific way by integer multiples of the coupling lambda. And this is weighted with some exponential p times zeta, thereby introducing some additional parameters zeta here into the answer, which are of course very important and which we will have to understand mathematically. All right, so this is very nice, and it would give us a very elegant non-perturbative definition as well as mathematical characterization of Z top if we knew the answers to the following three questions. We will need to know, of course, exactly how this quantization of sigma into a quantum curve should be defined and represented. Then we need to know how to associate the free fermion partition function to what we loosely call a quantum curve. And most importantly, and in some sense that is the main, say, subject of this talk, is we have to understand the relation between the variables zeta and t and the parameters of the quantum curve. Because only if we have this very precisely, we can, for example, hope to use a formula like this to extract from this thing here, which is in some sense easier to characterize and to calculate, to this object here, which is what we're really after. And for some cases, this has been worked out, well, relatively simple cases in the work by Dijkgraaf et al. However, I don't think that, well, even the general proposal for the class we're considering here has been formulated up to now. so here's the outline of the solution in some keywords to sort of advertise the main players in the game. So the goal is to provide a general and non-perturbative mathematical definition of the topological string partition functions for this class sigma. And we need to answer the following questions. I did it already, but I reformulate slightly here. How to quantize sigma and to turn it into a free fermion partition function. Modulo a certain modification, this has already been done in the work of Dijkgraaf, Holland, and Tsiolkovsky. But the most important point, and I think this is really new in our work, is how to parameterize the quantum curves in terms of these variables zeta and t. So these were these twist angles in t of the Kähler parameters. The keywords here is to use Riemann-Hilbert correspondence and abelianization. Abelianization is probably something we're going to hear more about tomorrow in Andy Knight's talk. That's the abelianization I mean. And then, well, to explain why this may be the right thing to do, I will discuss shortly, at least towards the end, why abelianization might be the right thing to use. All right, so let's now first quantize the curve sigma and then turn it into a free fermion partition function. That is the first step, step A in our program. Here's the curve, reminded, the equation of the curve. Now, well, using the symplectic form, which is naturally associated to the very defining equation of this curve, well, you would see that v and u are naturally canonical conjugate variables, so treating v as the canonical conjugate momentum to u, you would say v should become a differential operator, the differentiation with respect to u, up to order h bar. Well, h bar here was named lambda. So out of this curve, and that is, I think, pretty well known, we get what is called a quantum curve. For us, this will be the differential equation, which is written here in the box. A new aspect, and I will come back to this, is, well, we're not, unlike basically all previous works that I know, just taking here the curve, the quadratic differential, which was defining the curve in the first place. We do allow some quantum corrections, and these will be very important, and we will discuss them further. All right. Then associated is what is called a D-module. Well, if you don't know what D-module is, it doesn't matter very much. For us, it's good enough if you just translate it into a differential equation, namely just the differential equation that is here. But equivalently, you can think of it as being a flat connection, which in this case can be represented in this so-called upper form. So, well, it's gauge equivalent to a form where you have here zeros on the diagonal, 1 below the diagonal, and q, that is this, well, deformed quadratic differential, then above. And, well, okay, so you should look at the associated equation of horizontality, the equation for the parallel transport with respect to this connection, and the solution, the horizontal section defined by this connection, we call psi. And then it is basically a standard story, which was pretty well known. It was a story much studied, well, I think in the 80s even, or early 90s, is how to associate, well, to such a function, a state in a free fermion Fock space. The underlying theory is, well, the theory of Siegel-Wilson, this theory of infinite Grassmannians, and so on. But, well, I neither have the time to explain that, nor do I really need it. Here is a basically very explicit formula, which is then coming out of this theory, which, okay, the conceptual reasons for why you do that. This, of course, is what is explained by Siegel-Wilson in particular. But the formula is very explicit, right? So you're taking the psi, this psi here, which was the solution to the equation of parallel transport. You build here a certain kernel. Okay, it has a meaning, but let's not talk about it too much. You expand it, well, first in y, and then in x. This defines some numbers, these expansion coefficients AKL. You take a bunch of free fermions. Here we have some mode indices n and m running over integers, and s and t are running from 1 and 2, so it's for a two-dimensional vector space a basis. And then you form this kind of coherent state of the fermions created from the fermionic vacuum. So here is where the psi enters through these expansion coefficients. That's a standard construction, and good, we have defined the guy, and we quickly define from that the fermionic partition function that we're after. Which is what we do here. So the proposal is, and also this is not particularly new, the proposal is that the associated partition function is the tau function of Sato, Jimbo, Miwa, Siegel, Wilson, which we just get as an overlap, a matrix element in fermionic Fock space. We're taking here the state that we've just defined. The Q reminds that, of course, it was defined via the quantum curve, right? So the Q is this, well, the four quadratic differential defining the quantum curve. And we may act on it with some linear combination of generators of a billion subalgebras of the very big Lie algebra that is generated by fermionic bilinears, somehow to twist it, to introduce some additional twist or time parameters tau. And yeah, then we project on the vacuum, so we're getting some function of tau and q. Proposal, this is the sought-for function of zeta and t. But of course, here's one of the first problems. We have no clue what the relation between zeta t and tau and q is supposed to be. Okay, so what's nice about it is that what is built into this construction, it's basically tautological, is a nice relation to integrable hierarchies. And this has been extensively discussed also in the context of topological string in the work of, well, Mina, Dijkgraaf, Kumrun, and others. But so far, it doesn't really solve our problem, because on the one hand, the very choice of this algebra A, by which we twist here, is not clear. And second, yeah, the main problem really is to figure out the relation between these variables zeta and t, which is really what we want, and tau and q, which is what appears here. Exceptions are the examples that have been worked out by Dijkgraaf et al. All right, so coming back to the first point, which appears to be moderately new in our story, we have to talk about the quantum corrections in the quantum curve. So here is, at a glance, the modification that we propose. So there are some terms with some first-order poles, some terms with some second-order poles. This looks pretty arbitrary at first, but it's not arbitrary at all. First, notice, for example, there are some very specific factors here. 3, so it's of order lambda squared, and there's 3/4. We don't allow specific coefficients there. And secondly, these guys, especially the V's here, well, there should be Vk, it should have an index, never mind. These are related to the parameters which are in the Q0, which were, well, the deltas, the taus, the z's, and so on, by some equations which can be formulated like that. Okay, so two things you should notice, and this is what motivates this modification, which basically, when you think about it, makes clear this is inevitable, this is what you have to do, no way out. First, you may notice that if you just do the counting, I don't want to do it here, but if you do the counting, you will realize that only now you have enough parameters in the quantum curve that there can exist a mapping to our parameters zeta and t at all. Before, this was not the case. There were too few parameters. And second, well, these, if you know about a little bit theory of, well, ordinary differential equations, you will realize this is what is called apparent singularities, so the singularities of a very specific type. And what it means is basically that the D module, now thought of as the flat connection that is associated to this differential equation, this is gauge equivalent to a flat connection, a D module, which is completely non-singular at these points y equals uk. So this is just a gauge artifact, and it is one way to understand why they are called apparent singularities. All right, so we have done the first steps. We have a machine, thanks to, well, Sato, Jimbo, Siegel, Wilson, for associating to our quantum curve states in the fermionic Fock space and to turn it into partition functions. The main problem that remains is to find the relation between zeta and t and the parameters of the quantum curve. So the proposal in a rough form is that zeta and t will have a simple correspondence to very special coordinates of the monodromy data of this differential equation. What we need to make this precise are, say, two types of ingredients. One is the Riemann-Hilbert correspondence. Here, thought of as being the correspondence between monodromies or the holonomies of the flat connections, modular conjugation, and the D modules, the quantum curves. And second, well, of course, there are many ways to parameterize holonomies or monodromies. Well, it's the problem to introduce coordinates on what is called the character variety in mathematics. But there are some better than others, and these best possible coordinates for our purpose, they're defined through what, well, Andy and Lotte call a binarization. So it's basically a machine. I will review it very briefly, but hopefully Andy will do a much better job explaining that. It's a machine which, well, when we have our curve sigma, we can define very special associated coordinate systems for the character variety to this data. All right, here it comes, the lightning review of this method and how to define coordinates using the method of abelianization. But it's really just a caricature. I hope better explanations will follow. So, from the curve sigma, or more precisely the differential, one can define what is called a network. And under certain conditions, it takes a special form. It becomes, well, the conditions essentially are that the periods t, representing the Kähler parameter, are all real. Under these conditions, the Fenchel-Nielsen network looks like what is drawn here in black. Right, so you see here these black curves. So what it does is to decompose the surface C into annular regions. We have here our four-punctured sphere as an example. There's an annulus around puncture 1. There's an annulus around puncture 2, 3, and 4. And then there's an annulus separating the two pairs of pans. So this dashed curve here is a curve separating the two pairs of pans contained in the annulus in between. All right, so then the key observation for us is that any SO2 connection can be diagonalized within each annular region here that is defined by this network. So when we calculate parallel transport, say from one normalization point like here to itself or from here to there, it will be represented by a diagonal matrix. All right, so that is this. Well, the eigenvalues can be parametrized then in our setup in a simple way. I don't have the time to describe this in any detail. So they can be parametrized in terms of certain numbers. So we will just name them e to the I theta r. That's the notation for the eigenvalues of these, of what you can, what you will find in the diagonal elements of these matrices di, di prime, di double prime. So this comes from the parallel transport basically here in one pair of pans or the other pair of pans. All this is basically fixed by the e to the I theta r's. And there is one piece of data coming from, say, this dashed curve, which is the parallel transport along the separating curve. Also, it can be made diagonal, and eigenvalues are called e to the I sigma, so that is one more variable. And then there is a diagonal matrix describing parallel transport, say, from this normalization point to this one. So that matrix T here is again a diagonal matrix with eigenvalue e to the I theta. So this is, how the data are encoded then and how they will enter into a flat connection, which I'm about to define. What remains to be done is to describe, to explain, or to specify how we, what jumps we need to make, or what the connection matrices are in another point of view when we cross the walls of a network. Say, for example, to go from this normalization point to this normalization point, I have to cross the network. And this is where non-abelianness is coming in. And however, in this case, we're in the SL2 case, a fortunate coincidence is that we can show that basically these jump matrices can all be expressed as some non-diagonal matrices, which, however, depend only on the parameters we have already introduced, on theta, sigma, tau. Okay, so all this is just determined by consistency conditions like that we get one unity when we go around, for example, this little cross here. Okay, so then the game is simple. We can take any closed path where we want to compute the holonomy. Any closed curve gamma can be decomposed into segments contained in either the annuli or segments crossing walls, here drawn in green, or a path traversing the annulus between the two pair of pants, that is what's drawn in gray here, this line. What it means is I get a very explicit parametrization of the general holonomy matrices in terms of our parameters sigma, tau, theta, r. All right. So this is giving a very special way to introduce coordinates on the character variety, and why this way is better than others, I will return to a little later. Okay, so before that, I want to formulate our proposal finally in a basically precise form. So when we, well, usually these parameters T are complex. When we restrict them to reals, the Kähler parameters, that's what we want to do just to get these Fenton-Usen networks. Otherwise, they have a more complicated topology. I don't want to go into this very much. So taking such a collection of real parameters and a collection of these twist parameters zeta, the algorithm is to find the mirror curve sigma, a canonical basis for the first homology, such that the parameters T are just acycle periods of sigma. Okay. Then to find the Fenton-Usen network, which is defined by Q0. So this was what defines this sigma, which we parameterize in terms of T. So that is this gadget like what was drawn here in black, this network decomposing the surface into annuli. That's now defined. And then we construct the corresponding quantum curve associated to zeta and T, now identified via this dictionary with the holonomy parameters, right? So here, this is, well, part of the parameters T, we make it sigma r, or yeah, we identified with the sigma parameters. There is what is called the mass parameters in the gauge theory context. That is some other set of parameters. I mean, I don't really want to discuss this in too much of detail, but yeah, most importantly perhaps for us, these angles, well, these twist angles theta, which came from this segment, they're identified with a zeta parameter, which were the twist parameters appearing in this Fourier transformation relating topological string partition function to free fermion partition function. Well, okay, then the next step is standard. We'll construct the free fermion partition function as the tau function associated to the quantum curve. And then all we got to do is to expand in e to the zeta dot p in order to extract the topological string partition function. But of course, it's very important that here we're very precise about knowing what the zeta is. We could, for example, think of, well, I mean, redefinitions of zeta could often be absorbed into a redefinition of z top, and then it wouldn't give the right result. So we have to be very precise about that. And finally, okay, there was a restriction on T, but in the end, the result can be analytically continued in T. Yes. All right, that's a proposal. And there's a proof, at least in one case, that we can offer. And I really want to be quick, I guess, here. The proof is calculation of both sides and comparison. And in some sense, well, there's something beautiful and interesting going on in the proof, but I don't really have the time here. It's getting pretty technical. Let me nevertheless mention a few of the main ideas, or maybe a few points, briefly. So you have to do independent calculations of the both sides. On the one hand, you have to calculate the tau functions. And for that, what you can notice is that, in fact, the tau functions can be interpreted, well, basically in CFT terms, as generalizations of the conformal blocks for the free fermion BOA. The basic observation goes back to Moore. A variant, not on the language of conformal field theory, was given by Palmer, and maybe for the, well, generality or the context that we need here, well, I've given a convenient reformulation a little later, but yeah. All right, so having interpreted them as conformal blocks, we can use the standard tools from conformal field theory. In particular, in conformal field theory, we know we can glue conformal blocks from surfaces of lower genus, lower number of punctures, from, if if we have defined them on simpler surfaces, we can glue them in order to get the answer, the conformal block, on more complicated surfaces. So, well, the form that it takes is you have to sum over a complete set of states in the representation of the relevant VOA. Here's the free fermion VOA. And what this gives is, for example, some expression of this form. So here what is summed over is over pairs of Young diagrams and an integer n, which is the charge, which is just free fermion charge. And what is well known is that Young diagrams and charge label the states in the free fermion Fock space. And so this will give some piece corresponding to, say, a left part of the surface, and this will give some piece corresponding to a right part of the surface. So that's the general structure that you expect when you do the factorization as you do it in conformal field theory. Well, that's one way of doing it, and okay, so a vertex operator version of this way of doing it was described in the work with Jörg Teschner and myself. Another way, which came a little later, which ultimately is perhaps even nicer, I find, was done in the work of Gavrilenko and Lissovy, or Cafasso, Gavrilenko, Lissovy, which is more in the context of well, Fredholm determinants or the Siegel-Wilson approach. So it starts from the factorization of Riemann-Hilbert problems, and these authors have pointed out that it naturally implies a factorization of the tau functions, in the end, of course, of exactly the same form. And yeah, these authors have worked out the result, and that's what it gives. And okay, you realize already here the structure that we want, namely a kind of Fourier transformation. So this is our free fermion partition function, and here's the Fourier transformation, and this is what we want to identify with Z top, of course. Good. Here is the result in full glory, but really I don't want to talk about the details very much. Some of you will recognize it as something familiar. There is something here, the F's, which you can identify either with conformal blocks or in the Krasov partition function and so on. Perhaps one thing is worth mentioning. Well, what is of particular importance for us is are these factors here. The functions M, it's a kind of 3-point normalization factor which appears in front, for which there is an explicit expression in terms of Barnes double gamma functions. And it's important to know them very precisely for us. On the other side of the story, well, we can use, for this case, of course, topological vertex. So that gives a standard well-known algorithm. I don't think I have to tell you much about how to apply it. So there's a toric diagram for this particular toric Calabi-Yau. One, in the end of the day, has to take a scaling limit. But yeah, otherwise, there is the topological vertex associated to each of these vertices here. And for each internal line, there's going to be a sum over Young diagrams. The sums, like here, here, and here, can be carried out, and one remains with a sum over the Young diagrams Y1 and Y2, which gives it a structure like we just had seen before, like here. All right, so that's how it comes about. What has received perhaps a little less attention is these prefactors here, for which some care is needed. So if you want to get it right from the topological vertex, indeed, you have to be a little careful about then, well, that you get it right in the, before taking the scaling or geometric engineering limit, and then you have to take the limit, which is a little tricky, but anyway, we did it, and in the end, it gives just what we have seen before with exactly these M's. And, okay, from direction. So yeah, the upshot is we're getting the same formula, and it has the right form for representing or reproducing this relation between free fermion partition functions and topological string partition functions that Dijkgraaf et al. Had predicted. So I think an interesting application of this is that through this calculation, what we're getting is in particular a rather non-trivial quantitative check of the string dualities, which were going into the arguments of Dijkgraaf, Holland, Sulkowski, and Waffer. Because, well, you may simply notice that this is very sensitive to, well, in particular, these precise coefficients. So if they had not come out right, then you would not get here just the simple form of a Fourier transformation. I mean, it takes a moment of reflection to see that yeah, there's only very special sort of changes of M that could be reabsorbed into a redefinition of tau such that this form is preserved. There's very few options in which it takes this form, and the fact that the topological vortex calculation gives exactly the right coefficients for this to happen, I would call a non-trivial check of the dualities, because, well, it was comparing independently calculated objects, and it comes out in the right way. And furthermore, well, here also it becomes visible why really I insist that, well, the precise identification of this coordinate tau is very important because, yes, you could think of reabsorbing redefinitions of tau into G, and then G being identified with a topological string partition function would be different. It would give a different answer. So if we are to read it off from this formula, we need to know precisely what tau is. Good. I promised a few remarks on the question why abelianization is the right thing to use. I won't have the time for a very detailed discussion, but let me say the following. Well, the keyword is exact WKB. When we have real periods T, we get this, what is called Fencher-Nielsen network, which decomposes into annular regions as we exploited before. So that's what we consider. Well, then, what exact WKB tells us is that in each annular region, there exist unique solutions of the quantum curve equation, of this differential equation defined from the deformed quantum curve, which has diagonal monodromy. Well, this is what we do in abelianization to construct these preferred bases where monodromy or period transport is diagonal. Leading asymptotics looks like that, but okay, details don't matter right now. Namely, well, you can, of course, formally easily write out the expansion here in powers of lambda that is defined by some recursion relation. In general, this need not converge. However, in this case, what you can do is to Borel resum this expansion. This has been proven in the mathematical literature. And then doing this in this context and in this setup of abelianization, it is not hard to see that the analytic continuation across walls, because it is basically defined by these consistency conditions that I mentioned, that this analytic continuation is described by just the same jump matrices as are used in the abelianization framework. Well, and what this means, to basically cut a long story short, is that the monodromy of the Borel sums is most naturally parametrized by the parameters, the variables sigma and tau, which we had introduced. So this is the sense in which these are kind of optimal variables for the character variety because they make, in some sense, the connection between the picture in terms of differential equations, that is the holomorphic picture, the holomorphic connections, and the character variety most simple. It comes via basically Borel resummation. All right, so I'm already approaching the end. It seems I'm a little fast, but okay, it gives me time to say a few last words. So here is the summary. We have presented a proposal for a non-perturbative, and in fact, thanks to this story of factorization of Riemann-Hilbert problems and the associated factorization of tau functions, a pretty computable definition of the topological string partition function for the class sigma. That it is non-perturbative is something, okay, which wasn't quite manifest from the somewhat formal representations of the tau functions I've given before. However, in the theory, of, say, Siegel-Wilson, Grassmannians, and so on, there is a representation of the tau function in terms of a Fredholm determinant, and these authors, I would like to advertise their work. I think it's really beautiful and deserves attention. They have shown that, for example, the theory of isomonodromic tau functions and so on can be incorporated easily into this framework and then give such expressions, such factorization, such representations as we need here. Good, just to remind the key elements of the proposal, let's do it quickly. So we've given answers to these basic questions that I've asked: how to quantize sigma, turn it into a free fermion partition function. Well, we were using meromorphic operas. We allowed these apparent singularities to get enough parameters. And then what was standard and mostly well known, the theory of infinite Grassmannian free fermions. Then the main piece, basically, which I think is new in our proposal, is how to parameterize the quantum curves in terms of the topological string parameters, zeta and t. This was done through Riemann-Hilbert correspondence linearization, and it is doing the right job because exact WKB gives basically a canonical way to quantize the leading order result, the classical result, if you wish. Good, so, well, I don't have much time, but of course, maybe a few words are appropriate to compare it with the other approaches. Many approaches have been put forward to characterize and calculate the topological string. Most of the following, of course, is something that should be studied or is partly work in progress. Okay, first, in particular, integrability, in a sense, has already played an important role through the use of, well, Sato, Jimbo-Viva, Siegel-Wilson tau functions, where integrability is sort of built in because, well, using abelian subalgebras in this W1 plus infinity, we can easily generate commuting flows, that is, function which depend on, in general, an infinite number of time variables and therefore represent solutions to integrable hierarchies. So that is pretty old. In particular, I would like to mention, well, the work of Aganari, Jagraf, Clem, Marino, Wafa, who, for example, beautifully characterized the topological vortex in this way. And there's a lot of other literature using this. Andrei Okunkov seems to have, in the context of box counting, a very general picture, a very general theory for how to see integrable structures associated with that. Thank you. I think our point here is really to make this structure, which is not new, but to make it effective for computations or other means, other characterizations in complicated cases like class sigma, where I believe it hasn't been done. Topological recursion is another popular approach to topological string theory. To the best of my knowledge, for this class, so far, it hasn't been 100% clear in the community how to get started even with the topological recursion, how exactly to define the initial conditions in these cases. In other cases, it is well known, but in these cases, I believe it is not. And with a student of Bertrand Hinard, we hope to figure it out, well, soon, what basically we can read off from the exact answer that we have here on that, which then can teach us lessons maybe for even more general cases. Well, here, let me just advertise. One can discuss this in the context of the quantization of the moduli of complex structures on the Calabi-Yau and holomorphic anomaly equation. This is incompletely done. However, a remark one can make, and this was very briefly mentioned in the work we had with Jörg and Lissovy, is that this transform, which plays such a crucial role, has an interpretation as a Fourier transform relating natural representations for the quantization of the complex structures. So there is one representation on that side, another on this side, and this basically serves the task to diagonalize a natural commuting set of variables. So it has, part of that is already known, but I would say a lot should be done in this direction, and I think that could be quite beautiful and interesting. There's a relation to Hitchin systems. Okay, let me not talk about this. And of course, much of what we did, at least under certain specialization of parameters, can be also rewritten in terms of matrix models, that is in terms of contour integrals on the Riemann surface C. What is perhaps the most interesting aspect is that then, as we partly now understand already, the key issue of the proper identification of the coordinates gets translated to the definition of redefining the proper set, the good set of contours that does the job. Okay, I'm done basically. As an outlook, let me mention various generalizations that I think are mostly within reach, different levels. Toric Calabi-Yau should be very interesting to do. There is, of course, that is where we could work, could make contact with the work of Marcos Marinho. And say, as a hint that something along these lines can be done, I would like to mention the work of Jimbo Nagoya Sakai, which is relatively recent, our story was related to the isomonodromic deformations of, say, operas on punctured sphere. They have given a Q deformation of that story, where it's then the Q-Schlesinger equations or Q-Garnier system which appears. I'm almost done, thank you. Just 1 minute, perhaps. Well, higher genus, I don't think is a big deal. Irregular singularities, I don't think is such a big problem, but would be nevertheless interesting to work this both out. Higher rank is, of course, very interesting, because there one hits the problem that one needs to find the good coordinates, the analogs of these zeta and t, and that is a largely unsolved mathematical problem on which there was recent progress in work of Hollands and Neitzke, which will appear as well in the paper that we put out in the end of last year. And sort of as a philosophical end remark, I would like to say that what is crucial here is the interplay between two different integrable structures in the context. On the one hand, of course, the familiar and pretty well-known integrable structure associated to integral flows, Hitchin systems, isomonodromic deformations, and so on. But what's crucial here was to also take into account the integrable structure on the character varieties, which is best expressed in terms of coordinates of Fenchel-Nielsen type, and I tried to argue that there are some coordinates which are optimal for that purpose, defined through abelianization. Yeah, thank you. That's what I want.